So let's talk about amps, and not amps as they relate in general when it comes to electronics, but amps as they relate specifically to treadmill motors and treadmill motor installs.
Greetings, fellow DIYer, and welcome to my video.
If you've come to this video to get an electronic engineer's perspective on amps, volts, and watts, you've come to the wrong place. There is a lot of calculation that goes into amps and volts for specific components, and there are rules that have to be followed. What this video is not an accurate one-to-one, here's the ratio, here's the formula, here's how all this works. What this is, however, is more of a guide. It says, okay, this sort of works and this sort of works. This is why this sort of works. This is the downside, and it allows you to make a more educated decision. With this little bit of information, you're not going to know exactly how a change in amps or a change in volts is going to affect things, but you are going to understand enough to be able to make an educated decision. As with so many of my other videos, we are working with electricity. If you are not qualified to work with electricity, you can really hurt yourself, so use this information at your own risk. The first thing we need to understand is watts. Wait a minute, he just said we were going to talk about amps. Why are we talking about watts? Well, amps and volts are related. And because one has an effect on the other, a lot of things are rated in watts. Amps times volts equals watts. So the SCR voltage controller that I recommend in a lot of my videos is 10,000 watts. At roughly 100 volts, that is 100 amps. That's what it should be rated at as a max rating capacity. So that's the first part. We have to understand watts. This is critical, especially with budget-friendly power supplies. You always want to consider that the amperage or the wattage that it is listed at is maximum. So we're listed at 10,000 watts, like I said. And that means that it is good up to 100 amps. The rule of thumb when figuring out continuous amperage compared to max amperage is 1/2. So that would mean 50 amps is the max amperage output of that power supply for continuous use. The other thing you want to consider is a power supply that is rated for those higher amp numbers is going to have heavier duty components in it. And so it's going to last longer and be up to the task. Instead of pushing right up against the edge of what it's capable of and working it into the ground, it's just lazily doing its thing, and you're not at hardly any risk of burning anything out. Now, what does all this mean? What does an amp mean? What does volts mean? What do watts mean? Well, volts is simply how fast the electricity is moving. I have found that the best analogy for electricity is water. Now, I know water and electricity don't mix, but at least this gives you something that you can touch, you can feel, you can observe to understand exactly what is going on with electricity. If we have a hose, let's say it's a garden hose, and water is flowing through it at the rate of 3 feet per minute. So it takes 1 minute for water to flow 3 feet over the length of the hose. That is analogous to voltage. The lower the voltage, the slower it's flowing. The higher the voltage, the faster it's flowing. And that's all that is. It is the speed at which it is flowing. Amps is the size of the tube that's flowing the water. So think about this for a minute. Let's say these are pipes. The diameter of this pipe is a lot bigger. If we took a cross section of the water flowing, we are going to have a much larger area here than we are here. So that's basically analogous to amps. It's the ability to flow a massive quantity. Now again, how fast it's moving is volts, but just the size of the flow is analogous to amps. And there it is. That's why watts are so important. Because amps, how much surface area we have here, times volts, how much speed, how quickly it's flowing through, is going to create watts. And especially at lower voltages or at lower amperages, things don't always work the way they're supposed to until we reach a certain voltage or a certain wattage to overcome the resistance of the electronics. That is why amps and volts are related, and that's why watts are important. So why do amps and volts matter when it comes to a DC treadmill motor? Well, the reason we're all converting our lathes and other tools to a DC treadmill motor is because varying the speed is super simple. All you have to do is vary the voltage and you vary the speed. So how fast the electricity is flowing has a direct relation to how fast the motor is turning. So what about amps? What does amps have to do with it? Well, amps are what create the torque. It's the amount of torque that that motor can produce. So if you have a 12 amp power supply and you have a 20 amp motor, you, one, run the risk of burning out the power supply, depending on how things are set up. We'll come back to that. But two, even if it's set up so that you never can damage the power supply, you will never get full torque out of that motor. Now, I'm sure that there are some of you that are watching this going, well, I bought an aftermarket pulse width modulator and it's rated at 12 amps and my motor is 25 amps and it works just fine. Here's the thing. The load that the motor is under determines how many amps that motor is drawing. So when you fire up a motor, let's say it is rated at 25 amps, it may only require 10 amps to do most applications. Now, the moment you're doing something that has a lot more torque requirement, let's say you are doing single point threading, and there's a lot more tool pressure and it's causing that motor to kind of bog down a little bit, the amperage draw is going to go up. Now, it will not draw more than 25 amps. That's what the rating on the motor is. If you stuck that motor, it's not going to draw more than 25 amps. So that's why you can oftentimes use a lesser power supply and still be able to use it with a heavier duty motor. Now, some of those power supplies have built-in safeties so that you're not overloading them and you're not ever drawing more than the max output of that motor. But you have to keep in mind that you are leaving torque on the table if you are powering a 25 amp motor with a 12 amp power supply. So here's another issue. As voltage drops, the resistance of the coils inside the motor begin to reduce amperage. That sounds a little complicated. Let me unpack that for you. If we have a coil of wire and it's creating a magnetic field, that's what's inside your motor and that is what is causing the rotation. There is a certain amount of resistance that coil has. So as the voltage is trying to go through the coil, there is resistance. The water is trying to flow, but there is something kind of holding it back. Once the voltage reaches a certain amount, it's no longer an issue. It's pumping the amount of water that it needs. You're getting the total amps. But at the lowest voltage, oftentimes we have reduced amps. What that means is that even though a DC motor has a static torque curve, in other words, if that motor produces 1 foot-pound of torque at 1 RPM, it's supposed to produce 1 foot-pound of torque at 1,000 RPMs, straight across. But depending on the resistance of the coil, at those slowest speeds, maybe the bottom 5%, it will not be allowing enough amperage to flow through the coil at the lower voltages to have that 1 foot-pound of torque. And that is a curve that moves up. Like I said, maybe about the bottom 5%. Once you get above that, then it's a static curve. So the question is why? If volts are what controls the speed and amps are what controls the torque, why at the bottom range of voltage do we lose amps? It seems like they wouldn't be related. Well, again, we're going to go back to the analogy of water. There is a certain amount of resistance in the coil that has to be overcome before you get the adequate flow of electricity in amps. And the easiest way to overcome that resistance is with voltage. So the analogy would be like having a very small water pump and a hose that's running 100 feet up a hill. It's gonna take a lot of work to get the water pumped from the pump up to the top of the hill. And that's the resistance. And you're not gonna get a whole lot of flow. Now you crank that water pump up, you make the water move a whole lot faster, and it shoots up that hill and down the other side without any problem. And that's why we lose a little bit of amperage at the bottom, because that resistance, it restricts the flow, so it's not the big amount that we were getting. So that's where amps and volts are really important when it comes to treadmill motors. And that's why sometimes we lose torque at the lowest RPMs, because we don't have adequate amperage flowing through the coil because of the resistance of the coil. So we've talked about a 25 amp motor. What size fuse should I use? Well, if it's a 25 amp motor, we definitely don't want to go with a fuse that's bigger than that. So 25 would absolutely be the max. In most cases, I would put a fuse or circuit breaker in the system based on the size of the circuit breaker in your house. If it's a 15 amp circuit breaker, I would put a 15 amp circuit breaker between your SCR voltage controller and the bridge rectifier. If your house circuit breaker is a 20 amp, then I would put a smaller 20 amp circuit breaker between the SCR voltage controller and the bridge rectifier. You want it to be equal or less. So what about wires? Well, this wire, I believe it's 22 gauge, and this wire is 16 gauge. And with wire, the smaller the number, the bigger the wire gets. This is going to be able to handle a whole lot more amps than this is. It's no different than our water pipe analogy. The bigger the wire is, the more amperage can flow through it. If you undersize your wire, many things can happen, but the two important ones for this application are: one, you will restrict amperage, and so you won't have the torque that you need. And two, the wire will actually heat up. The electricity flowing through it, being forced through it, is going to cause the copper in the wire or the aluminum in the wire or whatever element the wire is made of to physically heat up. And that is a recipe for disaster. You can easily start a fire by having wire that is too small in your setup. When wiring up treadmill motor components, 16 gauge or 16 AWG is the bare minimum. 14 or 12 is going to be far better. When I'm doing projects like this, I will oftentimes just get an extension cord. That way I know what the rating is on it, and then I can cut it up and use it for the wiring that I need. I've had several people contact me about motor chokes, and they've ordered a choke that was not specifically a motor choke from Amazon, and they can't figure out why they don't have any torque or why their motor's not working at all. And the problem is the wire in the coil of the choke they purchased is so small that it is not allowing adequate amperage to flow through and power that motor. That's why it is critical that you use a motor-specific choke with your SCR voltage controller. And that's also why the advice that I've been giving for several years now is when it comes to chokes, bigger is better. The bigger, the more mass it has, the better it will be at cleaning the power up. And two, by being larger, it will oftentimes have a bigger coil of wire. In other words, instead of, say, 16 gauge, it's 14 gauge or 12 gauge. And that results in the ability of amperage to flow more easily through the choke. We've talked about how amperage affects motors. We've talked about how amperage can affect your power supply. We've talked about what wire size is important. But what does that mean when it comes to switches and relays? This switch right here is 30 amp at 12 volts DC. It's 15 amps at 125 volts AC and 10 amps at 250 volts AC. Now, there is no one-to-one formula. Like, if I looked at this and said, okay, 15 amps at 125 volts, and we've only lost 5 amps by doubling it. If we add another 125, we should be at 5 amps. But it doesn't work that way. The contacts inside this are specific alloys and rated for specific voltages, specific amperages, and you can't always just do the math and get it exactly where you want it. But what you can do is get a ballpark. I would feel relatively comfortable using this switch on a 375 volt system at 5 amps because it should function fairly closely. Now, you're going to want to check it for heat. You're going to want to make sure that it is not having issues, but I would feel fairly comfortable. And I would use the math to roughly get in the ballpark. But again, you're doing this at your own risk. This is just a general guide to understand. This was the direction switch for the treadmill motor on my lathe. And that motor is 25 amps. And that motor is obviously DC. And that motor is anywhere from 0 voltage to about 100 volts. And it says right there 30 amps at 12 volts. So this seems really undersized for that motor. And the truth of the matter is it is undersized. This switch lasted me about a year. I used it every time I threaded because forward and reverse were controlled by this switch, and that's what controls my ELS. And I've noticed in recent months that sometimes when I flip the switch, it does not make connection. That's because the connecting points inside the switch are starting to break down. And that's because of excessive voltage and excessive amperage going through it. Now, the good news is when I'm threading, I'm probably under that 12 volts. So we're well within the values of this. When I'm turning stuff at higher RPMs, this switch is already on. It's the on and off action that is hardest on the switch. When you get a little bit of an arc between the two contacts, that's when stuff breaks down. And because you're never throwing the direction switch when the lathe is turning, you're eliminating arcing. And the contacts are just basically carrying the load. Now, prolonged use at high RPMs is going to cause this to heat up and is going to shorten the life of this switch. That's why I have upgraded to the heavy-duty switch that you see in my recent video on my electrical control panel. The other thing, and this is where it definitely is less science and more ballpark figure, is this is rated at a much higher amperage for AC than it is at DC. Now, why is that? Well, AC automatically runs cooler because the positive and negative are flip-flopping 60 times a second. Heat is not as prone to build up in your contacts. DC is a constant flow of electricity, so any resistance in your contacts, any resistance in the wire will result in some heat. So that's the main reason that DC is much lower amperage, because for sustained use, 30 amps is what they say is max. More than that, too much heat is going to build up in this switch. But what's nice about the treadmill setup is we are using either a pulse width modulator or an SCR type controller, which is turning off and on rapidly to vary the voltage. So when we are at full volts, yes, we are basically full DC. We're not getting the back and forth action. But when we are at lower voltage, there's that off on, and that will actually help reduce heat in a switch like this. So that's a big part of why I was able to use such a small switch for over a year in my application. I hope this video answers some questions. I'm sorry I didn't have more on the bench, that it's just my hands sitting here talking. There wasn't a lot for me to demonstrate, but I really hope that this helps you figure out a better idea of what's going to work for your application.
If you like what you've seen, please click like. If you'd like to see more, please subscribe. Thanks for watching.